Dan Perry here with part 29 of our TCP IP basics. We're continuing with the OSI model, and this is our second part in the IP header. Again, we're examining the IP header. Again, only version 4 of the TCP IP header. Here are all the fields, and what we're going to be starting with today is the identification field. Move our way through specifically the most important area, the areas, the time to live, and the addresses. The identification field is used when a packet is fragmented. Most packets you don't fragment or you don't break into smaller chunks, but if you're fragmenting a packet, then you'll use this identification field. Fragmentation is when a device receives a packet and in the to the network, and the network it has to forward it to requires a smaller packet, so it has to break that larger packet into those smaller ones for that next transit. The maximum transmission unit defines those packet sizes. For the most part, we don't have to worry about it because we're dealing with Ethernet size packets. But if for example, we're going from, say, token ring, which allows a 32K packet size, to an Ethernet network, we would have to fragment the packets at that point. There are some flags there, 3 bytes. Bit 0 is always 0, it's reserved. Bit 1 is set at 1, saying don't fragment, saying, hey, this packet can't be fragmented. If you do need to transmit it, or it needed to be fragmented, instead you'll just drop that. And bit 2 indicates that this is a fragmented packet, and if it has a 1 in it and it says, hey, there are going to be more fragments occurring, or more packets occurring that is part of this fragment. The fragment offset is measured in 8-byte blocks, and that basically tells where in the unfragmented frame you're sending. So it allows for the fragments to be retrieved and then put back together. Your first fragment will always have an offset of 0. Possibly, aside from the addresses itself, the most important field in the IP header is the time to live. The time to live basically is the way we know if a packet can't be delivered. If there was no time to live, there might be packets that were bouncing around the internet since the 80s, but it gives a lifetime of the packet. Now, sometimes it's listed as being in seconds, but in reality, it is in the number of hops today, or the number of routers that it goes through, which is actually typically much less than a second. Every time a packet goes through a router, the router decrements the time to live. If the time to live reaches 0, then the packet is dropped and considered undeliverable. At that point, the router will send back an ICMP time exceeded message indicating that the packet was not able to be delivered. Different operating systems will put a different starting value from time to live, and it may be 64, 128, 254, which is the largest value, or 255 rather, which is the largest value. There are programs, and we'll be looking a little later on at programs such as Traceroute that can use this time to live to identify the path that a packet takes from source to destination. The protocol field indicates which upper layer protocol is used. The most common ones are TCP and UDP. That is a hexadecimal value of 6 or 11. And it includes a number of different protocols, including your routing protocols such as BGP and IGRP and so on. The header checksum is used for checking the header. The router calculates the checksum when it receives a packet, compares it to the checksum field. If they don't match, it discards the packet. Now, the checksum itself is figured in as a 0 because you don't know what the checksum would be until after you calculate the field. There are some routers, we found that some of the NAT routers do not recalculate the checksum if it's being sent to the final destination. Because the TTL time to live is decremented at each router, it has to be recalculated each time. The checksum is essentially what's called a ones complement of the ones complement of all 16-bit words in the header. Again, the checksum value is used as a 0 in that calculation. Don't worry about what a ones complement is at this point, but essentially it is a way of expressing a binary number. The address fields, both source and destination in IP version 4, are 32-bit values. Those 32-bit values for both source and destination, those are your IP addresses. In version 6, it would be 128-bit values. If you are using NAT translation, those addresses may be changed by a router, but unless you're using that NAT translation, which we'll talk about at some point in the future, those source and destination values do not change over the course of your trip. The options are not very often used in IP packets. They are in 32-bit word sizes. If you were using any options, it normally doesn't come out those options to an even 32 bits, so you would fill whatever was left after the options with padding to get to the 32 bits. Next time we're going to move down to our layer 2, our data link layer, and start talking about Ethernet frames.